The workhorse spacecraft has been circling our solar system's largest planet Jupiter since 2016. Here are a few things we've learned so far about the gas giant. Since NASA's Juno spacecraft went into orbit around Jupiter, it has slowly been coaxing the king of all the planets to reveal its deepest secrets. An astonishing catalog that includes daisy chains of continent-sized cyclones circling both of Jupiter's poles, vast hailstorms of ammonia-laden mushballs, a bloated, fuzzy core at the planet's center, and a convoluted magnetic field like nothing else in the solar system. Named after the goddess Juno, who was Jupiter's wife in Roman mythology, the spacecraft was launched in August 2011 with the goal of understanding the giant planet's origin and evolution. That story could have profound implications for everything else in the solar system. Jupiter has more mass than all the other planets combined. Its far-reaching gravity has shaped the orbits of planets, comets, and asteroids throughout the solar system's history. And its interior may harbor clues about what conditions were like when the planet arose from primordial gas and dust over 4.5 billion years ago. Polar cyclone party Juno is justly famous for its surreal photos of Jupiter's swirling cloudscapes. But while the probe does have an excellent camera, not to mention a fanbase of amateur Jupiter enthusiasts ready to transform its images into science art, what makes these photos truly unique is Juno's highly elongated, 53-day orbit. A trajectory that maximizes the spacecraft's science potential while minimizing its exposure to Jupiter's fierce radiation belts. Juno accomplishes both these tasks by coming in over the North Pole where the radiation is weak, whipping halfway around the planet at altitudes as low as a few thousand kilometers from the cloud tops, well below the strongest part of the belt, and then departing just 2 hours later through another weak radiation region over the South Pole. This path not only gets Juno far closer than any of the 9 spacecraft that have visited Jupiter before, it has also provided researchers with the first clear views of the poles, which reveal a sight not seen anywhere else in the solar system. Around the planet's south pole, Juno spied 5 cyclones, each wider than the United States, parked around a central cyclone of the same size. Not to be outdone, the North Pole revealed 8 similar cyclones encircling their own polar vortex. Remarkably, the storms didn't seem to be going anywhere. With each of Juno's flybys, the storms stayed put. And then in November 2019, during Juno's 22nd loop around the planet, it discovered that a new, smaller cyclone, merely the size of Texas, had sprung to life in the south and joined the others. It's not clear how these vortices form or how they stay so stable. Researchers hope to get a better look under the storms in the extended mission. The physics of orbital motion keeps nudging Juno's closest approach to Jupiter a bit northward with each orbit. In the years to come, that means the spacecraft will inch closer and closer to those vortices, enabling its instruments to get a better look. Complexity under the clouds because Jupiter is what astronomers call a gas giant planet. There is no point asking what conditions are like on its surface. It doesn't have one. Instead, the hydrogen and helium gas that make up the bulk of Jupiter's atmosphere simply get denser and denser the farther down you go, until the hydrogen becomes a liquid metal. But there is still plenty of action in Jupiter's swirling clouds, which are thought to be a mix of water and ammonia. And, as researchers have discovered via a microwave instrument that lets Juno probe beneath the clouds, there is plenty of complexity underneath as well. It turns out, for example, that the east-west winds that are known to tear through Jupiter's cloud tops aren't just a high-altitude phenomenon. The winds actually penetrate thousands of kilometers down. Likewise with Jupiter's famous Great Red Spot, a vortex a bit wider than Earth that's been churning for at least 2 centuries that astronomers can be sure of, and probably for much longer. It extends downward for about 300 kilometers. And then there is the case of the missing ammonia. We had assumed that as soon as you drop below the clouds, everything ought to be well mixed, says mission lead Scott Bolton, a planetary scientist at Southwest Research Institute in San Antonio, Texas. Jupiter is, after all, a rapidly spinning ball of fluid. A day lasts just under 10 hours. But Juno's microwave readings show that this mixing picture holds true only near the equator. It falls apart as you move north or south into Jupiter's mid-latitudes, where there is nowhere near as much ammonia as researchers expected. To see why, Tristan Guillot, a planetary scientist at Côte d'Azur Observatory in France, and others developed computer models of Jupiter's atmosphere and found that, away from the equator, ammonia might readily dissolve into water ice particles lofted up from below. This would reduce the amount of ammonia gas in these areas. It also means that the weather in Jupiter's mid-latitudes may feature hail-like storms of ammonia-soaked mushballs, frozen nuggets of roughly 1 part ammonia and 2 parts water. A humongous smeared-out center. Although Jupiter doesn't have a surface, researchers had a running argument before Juno's arrival as to whether the planet had a core, a solid ball of heavier elements gathered at the planet's center. They could argue it either way. In one common tale of Jupiter's birth, rocky debris slowly coalesced into a solid mass up to 10 times as hefty as Earth. The gravity of that mass then hoovered up all the gas in its vicinity, surrounding itself with the deep hydrogen-helium atmosphere we see today. But in a different origin story, a pocket of gas swirling around the infant sun collapsed in on itself, creating a more or less pure hydrogen-helium world without a rocky core. Juno seems to have ruled out the latter scenario, Bolton says. By tracking how the spacecraft subtly speeds up and slows down in response to variations in the planet's gravitational field, scientists have been able to deduce how mass is distributed in Jupiter's depths. And their maps show that Jupiter does indeed have a core, just not one that looks anything like what they expected. Instead of being a compact ball, the actual core is a fuzzy sphere spread across nearly half of Jupiter's diameter. We don't actually know why that is, Stevenson says. But I think whatever that explanation might be, it's telling us something important about how Jupiter formed. Things could have been stirred up by the impact of another huge protoplanet, he says. Or it could be that somehow Jupiter moved around and more planetesimals were added at a particular stage during formation. There are many different stories you could conjure up. Hybrid magnetism, Jupiter's huge fuzzy core, undoubtedly has implications for other aspects of the planet's behavior. One of them being the planet's unusual, contorted magnetic field. For decades, the textbook picture of the Jovian magnetic field was that it resembled Earth's, which is to say that it looked like the field of a really big bar magnet, with a well-defined magnetic north pole on one end and a well-defined south pole on the other. Quick peeks from earlier spacecraft seemed to confirm that picture. But the textbooks were wrong. Juno's measurements show that the magnetic field in Jupiter's northern hemisphere looks completely different from its southern counterpart. It's as if someone took a bar magnet, bent it almost in half, frayed one end, split the other end, and then stuck the whole thing in the planet at a cockeyed angle. In the north is the frayed end. Rather than emerging around one central spot, the magnetic field sprouts like weeds along a long high-latitude band. In the south is the split end. Some of the field plunges back into the planet around the South Pole, while some is concentrated in a spot just south of the equator. This magnetic field geometry is not seen anywhere else in the solar system. The southern hemisphere resembles Earth's field, which scientists call dipolar, because it has two poles. The north has more in common with Uranus and Neptune, where the fields are more complex. It was weird to have essentially one hemisphere Earth and one hemisphere Uranus and Neptune, says Kimberly Moore, a Caltech astrophysicist and a lead author of several studies of Juno's magnetic findings. Planetary magnetic fields are generated by electrically conductive fluids in their interior. The unusual fields at Uranus and Neptune may be due to these fluids being restricted to a thinner region of the planet, relative to their size. Something similar might be happening at Jupiter thanks to its dilute core, says Moore. The north-south dichotomy may also emerge from all this complexity. That can really change the geometry of the patterns you can come up with, she says. But that's just one idea. Helium rain might also wreak havoc on the magnetic field, as could penetrating winds. Giant distinctions. If Juno has taught us nothing else, it's that no two giant planets are alike. At first glance, Jupiter has a lot in common with Saturn, for example. But despite both being big balls of mostly hydrogen and helium, they've gone down quite different paths. Jupiter has conga lines of polar cyclones. Saturn has just one vortex per pole, one of which is six-sided. Jupiter's magnetic field is a hodgepodge. Saturn's is pretty boring. Jupiter's atmosphere is multicolored and banded. Saturn's is relatively unblemished. What do you think about this topic? Let us know in the comments.